So the group I'm affiliated with at JPL is the Origins and Habitability Laboratory. And it's a fairly unique group because it's kind of like a permanent research laboratory, where a lot of laboratories and research groups at JPL are sort of mission dependent. This one is not mission dependent. This one is like looking long term down the road. What does habitability look like on Mars and moons and other extraterrestrial bodies? And how does that reflect back onto Earth in terms of life origins on Earth? And so what we're doing in the Origins Habitability Lab is, one, we're trying to figure out, well, what does life look like? I mean, how could you use X-rays and a Raman spectrometer, which is basically just a laser? How would you know that you found life with just those two instruments? And that's pretty tricky, because what we see on life here on Earth is, how do you identify it on Earth? You look for things that are moving, you look for things that are growing. And when you go to Mars, you can't just, it's not that easy. You have to have some kind of spectroscopic signature of what is life, or what was life. Maybe it's dead and not moving anymore. How do you identify it? And so a lot of work that we're doing at the museum and at JPL is coming up with those sort of techniques to identify what is life, what's the biosignature of life, what is living or not living, and what are those tools able to do. So on Earth, bacteria that live in really salty environments, or live in like the high altitude alpine glaciers, they produce a chemical called like a beta carotene, which is kind of why carrots are orange, and orange feathers on birds produce these carotenes. And they're really, I think they're only known to be biologically produced molecules. So if you go to another planet and you find carotenes, that could be the nail in the coffin. And that's why I'm really excited about this next mission, is because they're flying to Jezero Crater, which is an old evaporated lake. And that's where our Origins Habitability Lab have been studying brine chemistry, biology, mineralogy for the last 2.5 years or so, is looking at what is life like in evaporating lakes. And carotenoids are a big part of it. They have to produce that. The bacteria have to produce these carotenoids to protect themselves from ultraviolet radiation. And there's a huge UV flux on Mars from the sun. And so we think that if something's going to live there for a long period of time, it's going to produce these beta carotenes, because DNA peters out after a couple thousand years. You just don't have much DNA left over. RNA sticks around for a bit longer. Lipids stick around for a bit longer than that. But it's these carotenes that can last for millions and millions of years. So these carotenes could be preserved inside minerals. They can be trapped inside minerals. And Jezero Crater is going to be a perfect place to look for that, I hope. Hopefully we'll be able to find some salts. I mean, that would be really nice to have to start with, that we're finding salts and we can identify these different types of salts. Next would be to find fluids trapped within the salts and identify what the fluid chemistry is. And this is assuming that we're not finding any life whatsoever. So it'd be nice to know what the fluid chemistry is, so that we can kind of figure out, would these fluids be sustainable for bacteria? Maybe they're too salty, maybe they're not salty enough, who knows what they are. And if there was carotenoids in these fluid inclusions, I'll be the first one to say, yes, there is life, or there was life on Mars. And that would be mission accomplished at that point. And so this is kind of like a broader sort of research topic of how minerals are like a fundamental part of understanding a lot of different things that are happening on planet Earth and other things, because Earth is 99.999% minerals. There's only a tiny little fraction of all the materials on and in Earth that are organic. And those organic things are really dependent on the inorganic mineral substrate. So it's bacteria that are interacting with the minerals, it's humans, you know, if you go all the way to the major megafauna, humans and other animals, they're living on a planet, living off of the soils that are harboring life. I mean, it's really a complicated web, but much of it really depends on the mineral chemistry. And there are scientists out there that I think that the mineral chemistry of a planet is kind of like a fundamental common denominator for what life can exist on that planet. That mineral content is probably the most important part of understanding planetary evolution and even life evolution. Mineralogy has a really big part of that as well.